All right, so I'd like to provide you with a explanation video for your radical operation homework. Um, use this appropriately. You should have already tried the problems, but you might want to watch the video as you work the problems, or maybe you're watching a video now that you're done. When adding, you need to have the radicals be the same. This radical here can't simplify or break down anymore, but this radical can. We can take something out of 24, that is a perfect number that's inside of there, that's the number 8. The 8 is going to come out as a 2. That's the root of 8. Now we can also take out a lot of this a. A3 comes out and becomes just a. Left behind is this 3 from the 24, and the a that was part of that a to the 4th. The good news is that now we've got a cube root of 3a and a cube root of 3a. So what I can do is I can add the I just realized that there's a little typo here, isn't there? Or is there a typo? I'm not sure which version you're looking at, but there's supposed to be an A right here that was on the outside. Now I can add my 2A and 2A. The intention was for that to be 4A, and then we end up with the cube root of 3A. So we'll go with that answer. How about trying to add or subtract in this case? Now, these are both square roots, so we're going to see if we can make them look the same. A9, there's a lot of that 9 that can pull out of there. 8 of it can pull out, and when x to the 8 pulls out, it gets divided by the 2 that was the root, so we end up with x to the 4th. It does leave behind a x that was left over from that x9. We still have a 3 out front. How about this 27? Now again, this is a square root, so when you think of the 27, you want to split it into 9 times 3, because 9 is a perfect square number, and the 9 is able to come out. Of course, when that 9 comes out, you take its square root, and it comes out as a 3. It does leave behind that 3, and that x, nothing happened to that. These are now the same, and it turns out that these are the same. I say it turns out, that simply means when I subtract them, then I'm going to get 0. I'm going to get 0 square roots of 3x, which ultimately is actually just equal to 0. Okay, number 3 is actually an easier problem. It's all right to have an easier problem at the end. Once again, I can split up 27 to be 9 times 3. The 9 comes out. When it comes out, though, you take its square root, so it comes out as a 3. Now, it's going to meet the 3 that's already out here, and we're going to end up now with 3 times 3. So ultimately, we'll end up with a 9 right there. So if I have 9 square roots of this 3 stays behind, now I can add the 9 and the negative 2. So we have 7 square roots of 3. When multiplying and dividing, you just need to have the same index. We do. That is, the 5s are the same, so we can just go to town here and we can multiply. Now, keep this simple. You just multiply the coefficients, but when you're underneath, you're going to multiply, and things are going to change a little bit. We're going to end up with a 30a squared. Now, are we able to take anything out of 30? Well, only if there's a perfect 5th root in there. What's a 5th root? We haven't talked about those too much. The only numbers that are perfect 5s would be like the number 1, and then 2 to the 5th, 3 to the 5th, 4 to the 5th. Now, 2 to the 5th is 32. That's already past 30. 3 to the 5th, now that's going to be a really big number. 3 to the 5th is going to end up being, geez, what is that? 3 times 3 times 3, yeah, 243. So anyway, there's no number that I can pull out of the inside because these numbers are too small to do a 5th root. Multiply Distribute, same thing, right? Multiply, distribute. So I'm allowed to multiply underneath, and when I multiply underneath, I get a 27, and also I add those x's and end up with x cubed. When I multiply underneath, we actually get 27 again, but we will end up with a x to the fifth. Now, we should be kind of wondering, is there anything that we can pull out of these? And in fact, there's a lot I can take out, because first off, 27 is a perfect cube root. So I can take all that out. That comes out to be 3. X cubed, well, that can come out also because it divides, and that ends up just being x. Now I can take out this 27. It does end up being 3 again. And I can take out some of this x5. How much of it can I take out? I can take out x3 of it. Of course, when you take out x3, it divides, so that leaves us with x to the first, but it does leave behind this x squared, so we'll still have the cube root of x squared sort of tagging along. Different kind of problem, but your answer is 3x minus 3x, the cube root of x squared. What do we got here? It's a multiplication problem. Yeah, you can multiply. You can do the 8 times 32. You end up with 256. Now, this is the square root of 256. Do you know your square roots? Do you know that 256 already is a perfect square? It turns out that 256 came from 16 squared. That means that when I take out 256, I'm going to get just 16. All right, and then we get into some of this advanced multiplying, where we really can just follow the examples from the front. That is, we can change both of these into rational exponents. The reason I change them to be rational is because I'm really trying to make these denominators look the same, but I can't just change them without also changing the numerators. So both denominators are going to be 6's, but of course, to make them 6's, I have to change the numerator. I hope you multiply by 2, so we get 2 6. I hope you multiply by 3, so you get 3 6. Once I have these both written as 6's, I'm able to switch back into radical form, and we end up with both of these now being 6th roots. Now, it's also the case that 4 squared is equal to, 2 squared is equal to 4, and 2 cubed is equal to 8, so that I can multiply these together to be 32. But it's really the 6th root of 32. This looks like a lot of fun, but still, what we can do is we can change to a rational exponent. I can change to 2/3. I can change to 1/4. And the whole idea here is to notice that your 2/3 and your 1/4, the denominators can both become 12s. Now, of course, I can't just make them 12s without also changing the numerator, but we'll get it ready with a 12. I hope you multiplied by 4. That would give you now an 8/12, and I hope you multiplied this one by 3. That'd give you a 3/12. Looks like that the problem is going to turn into the 12th root of 8 of x to the 8 and the 12th root of 2x to the 3rd. Now, I think I can actually do some math in here. I can change this to be 8x cubed, so that when I get to the business of actually multiplying these together, which you do want to multiply them together, they're both underneath, and they can be combined, then I can actually add the exponents to be x to the 11th. So we end up with the 12th root of 8x to the 11th. And then this last one, it's really a 1/3, and of course it's really a 1/2. So we end up with a 1/3 and a 1/2, which ends up giving you 1/6. But we want to write this as a radical, so this would be like the 6th root of 4.